long time. But now we're okay. So this is a special topic, nanothermites. It fits right into our topic. There's a lot of these with polymers. There's a lot of them with nanometals. There's a lot of them with nanometal oxides. So we're going to see a bunch of different things using these things. And we're going to actually see some different processes. Energetics has some interesting challenges of them. And so I'm going to start talking about basic combustion and what we're going to do here. So we had something similar to this where we had the solid to gas phase combustion. This is how wood burns. And so you have the gasification of something in the solid material. It has to go up and permeate into where the gas has oxygen. Then it can actually burn in the vapor phase. It's actually burning in the gas phase, but the back radiation is causing the gasification, constriction, and then eventually you're building a char. So that's how that works. However, it's a little different when you have a droplet. When you have a droplet, you have different phases. So if you have a droplet of fuel, and this could be anything that's a liquid here, you're going to have the fuel coming out, getting diffusing out to where the oxygen is diffusing in, and therefore there's a zone, depending on how fast this is diffusing out and how fast this is diffusing in, where the combustion actually takes place. So it never actually takes place at the surface of the droplet. It always takes place outside the surface of the droplet. And then, of course, you have your products coming out here. Now, again, one of the things that happens in the reaction zone is you have black body radiation going back to be absorbed by the droplet to help it volatilize even more. So it follows that similar procedure there, okay? So in both of these cases, the oxygen or the oxidizer has to diffuse into the system to cause combustion. Yes? Oh, I have several slides.
Okay, so because like thermite is, say something.
Right. Well, thermite is a specific type of reaction. And so I'm going to talk about how to the reaction and then some ways to process it, and some ways to test it, things blowing up. I even have videos of some of my research. Okay. So, but I wanted to talk about combustion because combustion and detonation are two different things. And so I wanted to talk about combustion first. Okay. So droplets, actually, this is like jet fuel or anything that comes out of the droplet. In fact, I published in this and where you can add nanomaterials to the droplet here. If they absorb IR radiation, it increases burn rate because it's the radiation is coming back, hitting those little droplets, increasing flame rate, and you actually can double the burn rate of a droplet with a nanomaterial. But I'm not presenting that. But, okay. Then there's technically solid phase combustion. And in solid phase combustion, you can have it where you are basically heating your material until it devolatilizes, and then it doesn't necessarily burn anywhere near with the thing you're heating. There's this thing called city gas, where they would actually take wood and heat it at about 500 degrees C, and it would just have the volatiles coming off in an oxygen-free environment, and then they would gather those gases and then combust them, and so that you actually have this entire thing taking place one place, and then the homogeneous burn taking place in a different place. So those are different than what we have when we have metals burning. Metals burn differently. There's three different mechanisms for a metal to burn in its droplet form. Number one, it burns where its oxide melts low enough or is brittle enough that it doesn't interfere with the combustion of the part. So your metal, like aluminum, is burning and produces aluminum oxide as it burns. And if it's got a porous surface, oxygen can still go through, heat can still go in there, melting the surface of the aluminum, volatilizing it, and letting it continue to burn. That's one mechanism, okay? So in that case of aluminum, it actually melts very low and actually has a fairly low boiling point for a metal. So technically it does burn in that reaction zone away from the surface of the molten aluminum. Now, take another material closer to, let's see, not magnesium. Yeah, magnesium actually does this. Magnesium has silicon. Silicon has a slightly higher melting point, around 1400. And what it'll do is it will start to burn and form a crust. Okay, and if it's burning irregularly, it will form an irregular crust, and you can actually burn all the way through to the center of the thing with this porous silicon dioxide coating right there. But if it actually slides out, meaning it actually burns slow enough to create a hard coat, it actually stops and leaves some of the unburned silicon. Then there's the last one right here, which is something like tungsten, molybdenum, some of the heavier metals, what happens is the oxide and the metal doesn't even melt because it's not in the high melting temperature. It might melt, but it barely melts. The oxide has such a high temperature that you have to just slowly have it burn through the oxide, permeate oxygen through the oxide to burn. So of the three of these, aluminum actually has a very high combustion rate. And silicon still has a very high combustion rate, even though it has that great surface and the oxide at the surface. So we have different mechanisms for what we have. Okay, and of course, in a gas phase, if it's already a gas, it burns in the gas phase with diffusion of oxygen. Why do I care about things like silicon and other metals? Okay, energy density. Okay, hydrocarbons have an energy density of 13 kcals per gram of fuel. Right here. So, for things like planes and cars and stuff like that, it's really good. But what if you want to do space travel or rockets? Well, now you start getting into things like magnesium, aluminum, and silicon. Okay. Now, beryllium actually has the highest concentration there, but it's actually not very common. And all the beryllium, most of the beryllium we get actually is used in some sort of flame type device. But it's fairly high in the energy density. The system. But most people use aluminum, silicon, and magnesium because they're cheaper. And they have about the same energy density for the set right there, with aluminum and silicon being the best. There is an advantage to silicon though. Okay? Silicon creates a very thin oxide layer, 1 nanometer or less. Think about all your perfectly, level, crystal face, wafers you get. You can have them 0 oxygen, move them around from here to there, and put your layers on there when you want them, or etch it so you have an oxide layer on there. Aluminum forms a 20 nanometer oxide layer within hours of being exposed. Okay, so if you have an 80 nanometer aluminum particle and it has a 20 nanometer shell on it, you just destroyed 45% of your burnable material. If you have an 80 nanometer particle of silicon, and you have a 1 nanometer thing, you have 98% of your combustible material, and they have about the same energy density. So silicon actually turns out to be a really good choice for using it as a metal fuel. Now, why do we want nano instead of micro? Well, part of that is surface area. Okay, the more intimate you get your oxidizer and your fuel together, the better it will burn. And if we think about an explosive TNT, I have the mass balance equation here, is that the only reason that that is such that it burns so quickly is because it has to eat the right amount of oxygen to nitrogen to carbon to get it to completely rearrange and turn into gases. Okay? And so it doesn't have to scavenge, it doesn't have to wait for oxygen to diffuse in, it has all the oxygen it needs. So all it needs is a trigger. And it will immediately go to its gaseous layers and go. And so that's one of those things. So this one right here, oh, we got to do it on my laptop, sorry. Because, not that one, over here. Sorry, there it is.
Is it recording?
No, it is not. Yeah, it is recording. Yeah. Okay, not that one. Okay, come on. It is recording, so that's good. Okay, MSEC. The movies are only in the come on. Okay, let me try it this way. Reset. Okay, I'm going to stop sharing this screen and start sharing this screen. Let me get down to the right slide. There we go. There we go. All right. So let me share my screen with that one. There we go. Okay, and we're going to, oops. Try to get this as big as possible. Let's see if it's going to mess everything up doing that. No, looks like it worked. All right, so this right here is a combination of silica nanoparticles, 80 nanometer silica nanoparticles with a 1 nanometer layer of oxide on it. And it's going to do an exchange reaction with copper oxide. Okay, which means silicon wants the oxygen more than the copper. And so what they're going to do is they're going to exchange the material. So the copper oxide is 20 nanometers, and actually the silicon in this is micron sized. It's micron. It's about 1,000 nanometers. Okay, and so I'm going to start the movie here. So this has a lighter wire.
It's burning, but it's also flesh. Come on. It's definitely something boring coming off. It's better than that little tasmanian.
So I consider that poor.
It's making the carbon, it's making the silicon chloride, and that's reacting with the humidity in the air.
Okay. If we switch over to that's the same one. And if we switch to a nano material, this is 80 nanometer silicon with copper oxide.
All right, this is silicon with copper oxide control. No flux. Armed. 3, 2, 1, fire.
So micron doesn't burn very well. That one almost looked like it exploded, right? So that's why we're interested in these nanocomposites, is because the more intimately you get your oxide or your oxidizer, and we're not going to just use oxygen or metal oxides, the more intimately you get the mix, the more reactive they are. So I'm going to go ahead and stop sharing and move back to the iPad and in show. And hide that. Share. Okay. Okay, so that was the difference. And so that's why we want to look for this. There's also a concept associated with this. It's called a metastable intermetallic composite. You can use these in a bunch of different ways. For example, boron and titanium, actually, they form a very energetic blend when they mix together. And metastable means that you can process it until one of the components melts. Once one of the components melts, then it's going to react, it's going to blow up, and it's going to be gone. So this is actually one of those reactions, is the thermite reaction. The thermite reaction is taking powdered aluminum and iron oxide. And so your oxide is coming from the iron here, and the aluminum is now technically your fuel. And so what happens is we put the aluminum as a solid, and this is a solid. If you get any of this aluminum molten enough, it will start to react and pull the oxygens off the iron, reducing the iron to iron 0, or iron liquid here, molten liquid here, and aluminum oxide. And it does it very quickly. If you look at micron-sized powders, they used to use these to actually do fixing railroad, tying 2 ends of a railroad together. They literally put this little cup of it, run the thermite reaction, and the steel drips down in between the 2 rails and it fuses them together. Okay, so that's the most common industrial use for this, but in the military, we use it more for energetics, pyrotechnics, and propellants. But it's a really cool reaction. So this reaction, this thermite type reaction, where we have a metal oxide and a fuel, means that they just switch oxygen and give off lots of heat. Look at here, this has a negative enthalpy of forming of 1,669 kilojoules, and so this is forming right here. And so it actually gives off a lot more heat, double the heat, than just oxidizing the iron by itself. So because it gives off so much heat, double the heat that the iron oxide would have, it's got a thermodynamic driving force to have the aluminum be consumed as the oxide and the iron being produced as the metal. Okay, so it's not just like a crazy reaction, it's thermodynamics at its finest.
And how much energy does it need?
This right here, you have to melt the aluminum to start the reaction. Okay, so most of the time when you do this, you either use a methane acetylene propane torch, or I see the other way to do it is you take a piece of magnesium, put it in the middle, light the magnesium, and the magnesium will start the reaction and melt.
So as soon as it will get in contact with the electrolyte, it will start burning, right?
Right. And so what it's going to do is it's going to start burning typically from the middle, and it's going to slowly burn outward. Again, the heat being absorbed by the aluminum to melt it, making it react. And then the iron is going to be dripping, you know, going slowly down through the middle of the pile. And so at the bottom, if you don't catch it, like if you have a mesh there, you get the liquid material just drip down.
The reason that's just because you're just trying to overcome the activation energy. It's not because of melting itself. It's like physical.
My understanding was that you actually want to have the aluminum melted so that it will start to do the reaction.
Just due to the heat.
Right. Yeah.
I had heard of one of the vendors that used aluminum fire. It was because they were deburring sheet metal. A machine that just like sands and burns sheet metal, but over many years of not cleaning the machine, somehow it can hide it.
Yeah.
Power.
Most shops have non-ferrous and ferrous workshop areas because aluminum will do it, magnesium will do it, a lot of your softer ones, some of your nickel alloys will burn too. In fact, I'll show you a slide. I can burn any metal. Just let me get it small enough. I can burn it.
Yeah, so there.
I can get it. I can burn any metal. Okay. So now we have these interments, and in fact, there's even one of the more famous ones is a nickel. I want to say it's nickel and iron, but it might be nickel and cobalt. But what they do is they lay down a layer by metal deposition of nickel, and then they lay down a layer of steel or cobalt, and then you just do that back up. You just keep doing that layer by layer, and if you stab it, it forms an intermetallic complex. So it's metastable because until it has a stress. When you stab it, it actually makes an alloy and gives off massive amounts of heat. Looks like a detonation. Okay. So I said this is qualified as a pyrotechnic. So let's talk about the difference between high explosives and energetics. So energetics is just anything that gives off a massive amount of energy in a fairly short period of time. Okay. Now they are defined by their time regime. So we have things like low explosives. Black powder, flash powder, smokeless powder. That's actually used as a propellant in most weapons. Most guns that have cartridges have black powder or a smokeless powder. Sometimes it's called a binary compound that they use in there. It's just nitrocellulose, nitroglycerin, and a little bit of carbon to dissipate static electricity. But we consider those low explosives, and I'll tell you what that means in the next slide. But then we have what we call primary high explosives, which are things that detonate and create a pressure wave. And when they detonate, they go off. And the primaries are very easy to detonate. So you've had those little sapling pops, thrown around. That's technically a primary because it's easy to set off. Now, once you go to that, you have secondary explosives like TNT and RDX and stuff like that. And these tend to be for what the main charge is, but they're harder to set off. So with TNT or plastic explosives, you actually have to have a blasting cap, which is a primary, to get it enough energy to start it propagating. Okay, so I said there's a difference between those, okay? And explosives versus pyrotechnics versus propellants is all about the 3 Ds, okay? It's all about the time regime. So if we look at this first one right here, 1 millisecond after it is ignited, it's at its max pressure. So now it's pushing everything out of the way, and the pressure wave or the detonation wave is usually faster than the detonation, than the shock wave. So you can actually have 5 miles of det cord, and it actually goes at about 2 miles a second. So you can watch it start here and end there, because that det cord, the entire 5 miles will go off in 2 seconds. Okay, so that's detonation velocity. And so when you have a detonation velocity that's big, you have a very big spike in pressure. Now, on the other hand, a propellant, we don't want that, because that's just going to blow up your rocket motor. So what we want is this slow rise to a max pressure and then a consistent output right here. So propellants are designed to not have a percussive wave or a shock wave coming out of it. It's just having a burning front that's consistent. And so here we have a propagating flame front. Now, usually they burn very fast, and they're putting out lots of gases. And so that's where we get some of the thrust from it as well. Now, deflagration, or what we have is if it's a slower decomposition, and your primary goal is to put out smoke or light. Your primary goal is to put out smoke or light. Think of you know, a concussive grenade where you want like to be all smoky when you walk in the room. That's where you go for pyrotechnics. And those, you actually have a much slower wave, but you're not trying to just generate gases like you are here. You're actually trying to generate solids, like aluminum oxide, or a lot of the experienced use organic materials because it makes a deep white smoke, like naphtha or something like that. Okay, so do we understand the difference between the types of energetics? So what we're going to look for in this is we're going to look for 2 things in our materials. We're going to look for a detonation velocity or a shock wave, or we're going to look for burn rate. So there's a bunch of different tests we do to do these burn rate systems. Okay. So the first one I want to look at is, this is a review of mechanically prepared reactive energetic materials, and they use several different methods for doing this, and then they compare other methods as to what the energy density of the final materials are. Now, if we think about it, a shaping ball mill would be a good way to incorporate materials, right? It's going to grind them slower, and it's going to grind them smaller and smaller and smaller until you stop going. Okay, so that's going to do some interesting stuff. But if you wanted a slightly better grinding process, you go for the planetary mixer right here. So the stage is actually rotating, well, each of the cups are rotating in an opposite direction. And so you get a different type of grinding. These tend to have a lot of actual pressure. When you go from end to end, the ball hitting the other end might have enough energy to detonate your material. So the planetary mixers actually do better because they more roll along the sides. They're held on the side of force, so they do a much better job. But the advantages of this are that, you know, they're very easy to find. Again, they're pretty small, so this is kind of lab scale right here. But we're looking at, you know, if you're going to do lab scale, you're going to use that. It's not good for, you can't do that kind of ball milling for an industrial purpose. However, you can get these pretty big, around 500 mils, and these are safer, but they are still a batch process. But if you really want to go high, you go for an arbitrator, agitator, yeah. So you have your vessel, you have your milling material, and then you have an agitator in the middle that agitates them. And so this is actually pretty good because you can go all the way to 400 liters right here, and you can look inside it, you can cool it, you can see, you can monitor by. The only thing it really doesn't do well is it doesn't seal well, and you're exposing your materials to atmosphere. So if you had micron-sized aluminum when you started, and then you ground it to nano-sized aluminum, and then you open the thing, it's going to go poof, because the surface area.
These layers of materials, the particles are very tightly connected with each other. Do you think that they can detonate with themselves?
The particles are the balls.
The balls.
So this is actually sort of a little overfold. There's a little more space there because they have to move when the stirring happens. So they kind of go up and down as the arms go past. Did that make sense?
Yeah.
Okay, so in this one, they wanted to look at those right there. And so they also came up with this concept. There's what they call arrested reactive milling. Okay, so let's say you're getting your stuff, you know, to put in there. It's a bad mixture. You know, and you start just doing your milling. Eventually, it's so intimately involved that all you need is one errant little ball to give enough energy to actually set the thing off, and you end up burning off everything you just created. So what's happening here is you have a mixture of larger particles. You're getting much smaller particles, and you're activating everything by giving it a higher surface area. But if you go too long, it destroys itself, and it turns into the aluminum oxide and the iron metal. Okay. So what they do is they actually start and they make sure they get close to the failure point of the material. And then this is the most activated, highest reactive material they have. So this is a little bit different, but it uses a shaker ball mill. And so if you're thinking about that, if it gets so good that it's really high energy, and then the ball itself hits the end, it's enough energy to set it off. So it's tribologically induced. I need to mute my watch.
So the aluminum melts in that?
Not during the milling right here, but during this part right here, that's where there'll be molten, or at least a high level of oxygen exchange between whatever oxide it is and whatever it is.
So is the idea to mill it until it gets to the nanocomposite state and stop?
Yes. And you can go to a couple different ways. You can add solvents to help cool it down, to keep it from doing that. You can add, and that dilutes it out, and when the solvent evaporates, you have your nanocomposite. You can also add what we call binders. And I'll have actually 2 special ones with just binders. And those typically are polymers. They'll kind of keep it all clumped together too. So when we do these, you can actually see the energy release on these different systems. So the way to read this graph is that this is the energy right here, the delta enthalpy of oxidation per kilogram. So that means that all of the metals are right here on this thing. They do not have a delta H of reduction. Okay, they are just being oxidized by air. So that's why they're all here. And so titanium doesn't have as much energy as zirconium, magnesium, and aluminum are really high. But look at lithium and boron. Okay, well, it's kind of cheating because it's kilojoules per gram, not kilojoules per bomb. Of course, those are much lighter metals, which is why they're semi-metal in the case of boron. So that's why they do it. But if you take boron and mix titanium with it, it actually makes an intermetallic complex. And it does actually react and give us a lot of reduced energy. So the further out you go here, the more energy is released during the reaction. Okay, so the more energy is released during the reaction. So if you're looking for is 8 kilojoules per gram or 10 kilojoules per gram. So that's really good. And so when we have our nanomaterials with an oxidizer intimately mixed with a unoxidized metal, you get these high energy systems, lots of release very quickly. Okay. So, and if you look at one of the other ones in here, so here's the aluminum copper right here. So depending on what your mix ratio is, how much copper oxide you have versus how much aluminum you have, changes that output. And so that's why these lines are kind of moving out here. So this is the iron. This is the one that's the standard thermite one. And then we also have a couple crazy ones like bismuth and tungsten. Bismuth and tungsten were used originally because they wanted, per unit mass. But it turns out, the tungsten and the bismuth are both very heavy atoms. So you have very little oxygen for a lot of mass. So that's why their energy density is lower. So that's why they're closer to this, the starting point here. But see, now we have, we've taken away all the heavy elements. We only have light elements, and we're using a nitrogen to help bind our oxygens. We're getting to a much lighter per unit of oxygen, much less dense. Okay.
So I got a question.
Okay.
Why are the ones on said that the higher the more negative that would be a reduction?
Mm-hmm.
But isn't obviously it's we're oxidizing the aluminum.
Right. So we're oxidizing the aluminum, and the enthalpy of oxidation for aluminum is right here at 30. So we're going to have minus 30 here plus
right.
the reduction over here. So the two things added together is the total.
Still,
So we have, and again, these slope downward because you have fuel-rich mixture, and then you have an oxygen-rich mixture at some point. So there's some balance in between there where you get perfect exchange.
It said that what would be the proportions?
It depends. Well, you can do it stoichiometrically, but it's never really that way. So you say, okay, I have for like iron here, like copper oxide. That's 1 oxygen and per copper, and aluminum wants 3. So this is going to be a 1 to 3 to give you stoichiometry. But I bet it's not 1 to 3. It's going to be somewhere near there. So you're transferring as much oxygen as possible, but there's some intermediate where the heat is given off much better. Sometimes it's high, sometimes it's low. Most of the time it is fuel rich. Or you change your oxidizer, which we're going to do. Okay. All right, another way to look at that is this is the milling dose. So how much you can do. And there are kilojoules per kilogram here. And again, we're getting a very high enthalpy here of reduction right here. But again, we don't have a good milling dose. So because we have the organic materials here, the lighter materials, we have the metals without oxides showing up on this side here. It's just another way of looking at where is the energy coming from. The energy is coming from the other side. Oh, wait, is there? It's not a different one. Okay, so their idea of how this kind of works is that you can actually have your grain as created is going to be a blend of your aluminum matrix right here, some of your oxidizers, and then there's going to be grain powders. Okay, and if you heat it up slowly to the point where the aluminum or the oxidizer melts, we're going to change the surface area now. Remember, everything when it melts wants to go to a sphere, so it minimizes its surface area. And so you're going to have these inclusions of maybe not melted material in your aluminum. So at a low heating rate, you can actually get poor burning. Okay? But at a high heating rate, you're going to get oxidation because now your metal is reacting right at the surface of here. You get more surface area of your oxidizer, and you actually have the places to vent any gases you're giving off where the grain boundaries are. Okay, so what does this look like in reality? Since that's a really cool graphic. All right, so if we look at this one right here, this one was done with a high heating rate. Okay, we can tell this because all the little pools of oxides or copper are scattered all over the place. There's little teeny bits everywhere. Okay, that's telling you that we had a bunch of different little fragments burning all at the same time. In fact, it burned much faster. If you have a slower heating rate, you get a big chunk of aluminum oxide sitting on a big chunk of copper. Okay, and so this gave, the reaction was much, much slower, gave off less heat per unit time than this reaction did. And this reaction gave off more heat per unit time, and it gave that diffuse structure to show you that it had practically exploded as it burned. Okay. Okay, so I think that's the last one for that one. Yeah, so now we're going to go, I thought I'd throw in something with graphene in it, just because graphene's our friend. So this is an iron oxide aluminum, so it's a thermite-based reaction, but they're using graphene to help transfer heat and make it set off faster and or eliminate electrostatic discharge. So if you have, if you had a cat, you could actually build up enough charge on your finger to detonate something with electrostatic discharge. So all benches are grounded and have conductive mats and conductive floor mats, and conductive shoes and conductive lab coats, and they're all wired together. It takes about 20 minutes to get all your clothes off. But in here we have a nice aluminum particle, and these are freshly made, and it has a 3 nanometer aluminum oxide coating on it. Okay, so it's not metal to the oxidizer. Then they actually grew the oxidizer in a solution and then they added graphene, reduced graphene to it. And what they ended up with is, so these are the little graphene dots, and then these are the iron oxides deposits on the outside of the aluminum dots. And with the graphene sheets, they're also helping tie. So now you have an intimate mixing of your iron oxide, your graphene, and your fuel, which in this case is aluminum. Okay, so what did they see? Well, what they saw was when they did it as an assembly, as a self-assembly, where they alternated the different materials right here, they got a very sensitive material right here as they increased the graphene rate, except for this one outlier here. It was a very insensitive material, and it was the highest energy density material. So we have a benefit here in the fact that the graphene is at the perfect level to dissipate any electrical stuff, but not inhibit its reaction. Now, these are the ones that are done with self-assembly, and this is one that was just a random mixture of graphene oxide, iron oxide. So they're saying that having it grown such that you have aluminum with the iron oxide and the graphene in that order is better for the system and allows for you to have a higher higher safety factor in the system. Okay.
Not really like, I guess it's a composite, but it's not distributed. It's like surface contact.
Right, but so if you think about it, and then whatever like stuff that is not stuck to the outside fills the place. So it's not a polymer composite, but it is a composite. It's a layer, spherical layer. Okay, so they reviewed a whole bunch of these and looked at different ways to do assembly and then looked for their energy output. So in the first one, they had a layered powder right here. It was 80 nanometer powder, and their oxidizer was a nanopowder, and they self-assembled them. So that's the copper oxide and whatever. With the magnetron sputterer, what they do is they put the aluminum layer first, then they put a copper oxide layer, and they can keep stacking it up until it's a bulk material, which of course is very expensive, probably not good for production. But there is an option for this because eventually we're going to do MEMS with these, looking at, and I'll talk about that. So there might be an opportunity for that. In the next one down, we have magnetron sputtering to get to the nickel iron oxide frameworks. We have sputtering solvent mixing right here. These are iron oxide nanotubes, and these are rectangular sheets of the molybdenum oxide. So they're almost like graphene. And they were doing solvent mixing, and they have really good energy releases here. And then by going to the larger molecules like the bismuth oxides, even though they're just almost not in the range of nano, they're still giving us a good power output. And then this is the one that they did, saying that they did it by atomic layer deposition, and they had a low onset temperature, which means it should be easily and safely detonated at 400 degrees C. Okay. All right. So that's what we call, that's a layered self-assembly method. Right here, we're alternating, the graphene oxide, the ferric oxide, and the aluminum. Well, there's also a way to do it with sol gel. I'm actually going to show you about 5 different methods. This is sol gel right here, and UFG is the worst acronym I can imagine, but it stands for ultra fine grain, which is 20 nanometer aluminum, 25 nanometer aluminum. And then they created what are called zero gels and aerogels. Okay, so the difference between a zero gel and an aerogel is a zero gel is dried in ambient conditions and usually has less porosity than an aerogel. Aerogels are usually dried under a special process that gives them porosity above 80%. So usually zero gels are around 50% or less, aerogels are 80% or more. So they made both. They made an aerogel and a zero gel for these things using the same thing with the aluminum particles, and they wanted to show their aluminum particles are still crystalline. And then they had iron oxide particles that they put in there as well. And then they did a process to get it to be a aerogel. Okay, so the way they did this was they did the zero type by sol gel. So they put in iron and they slowly converted it to iron oxide to generate the matrix. So they had their aluminum suspended in it, and they were able to see that when they were able to do this, they got good surface areas right here. This is by BPT, measures surface area by absorption of nitrogen, the surface. And so really for aerogels, you can go all the way up to like 1 point, let's see, 1,600 square meters per gram. They can get very high. Pore volumes are okay, and their average pore sizes are pretty small. Those are in nanometers, so their pore sizes are small. And then when they took the zero gels right here, one with micron-sized aluminum and one with the ultra-fine grain, the nano aluminum here, they saw that the safety of this actually had increased right here. DH stands for drop height 50, okay? So drop height 50 means that you drop a set of things, and if half of them blow up and half of them don't, that's the right height. The gold standard is TNT, trinitrotoluene. It has a drop height of 50 centimeters. Okay, so it has a drop height 50 of 50 centimeters. Okay, so what we're saying here is that you can drop this 3 times higher and have it not detonate. So it's 3 times safer than TNT. Okay, spark does not set it off up to 1 joule, which is actually a very energetic spark. And friction does not set it off at 36 weight. So you put a 36 kilogram weight and then you pull your material underneath it and you can get tribological detonation. So they pass all of these safety tests by turning it into this aerogel.
Can you explain the droplet again?
Okay, so for safety, they do a drop height test, which is, so literally they take a sample and drop it from different heights and figure out where it stops reacting. So let's say you've got some TNT and you start dropping it here. Well, none of them will go off because that's too low. But then you got it up to 50 centimeters and about half of them will go off. Okay, and above that, all of them will go. So that's the height you can drop an energetic material and have just the weight of its own self be able to detonate the material. Okay.
But in friction, I would say.
And yeah, friction, you also can detonate things. Anything that breaks a crystal gives enough energy to break, or a spark. So in friction, we call that tribological detonation. And if you can think about it, every time you break a crystal, you're giving enough energy. If you're breaking a crystal under shear, and it has enough energy to detonate the material.
They are very sensitive, dropping them from like 4 feet.
Well, I mean, that's right. That right there is 149 centimeters. That's over 1.5 meters tall. So that's what, 9 feet, 8 feet. So it's pretty good. So I mean, obviously, you want to have a safe material but energetic material at the same time. So there's always a balance between those two.
Okay, and you can also probably use measures to prevent a really sensitive material from prematurely.
Right, and then you give it to some guy who just got out of high school in the Navy, he drops it on the deck. So there's a certain amount of preventative measures for trained experts, but then there's also, you got to plan for the worst case scenario too.
What's the test setup for like that friction?
Oh, let's see. I want to say it is literally 2 pieces of the same material, not rubber. It's going to be a harder material. They put a weight on top of it. They put some material in here, and then they slide one of them. There's also another, there's another setup where they actually have a pendulum that'll slide across. But I don't have any pictures of that. So this is a cool picture because look at this. This is this entire chunk right here. They made this square thing in sol gel. They basically poured everything into a cup, let it run overnight, and dried it right here. And then they're hitting it with a blowtorch up here, and the surface here is starting to catch fire. But notice all the little sparky things. Little sparky things are the aluminum burning in the hot gases of the blowtorch. But I thought it was really neat that this is a macroscopic size material here, and it gives this nice little behavior. Technically, this is not a detonable material. I would call this a pyrotechnic material because it does give off plenty of light. Okay. All right. So we've done a lot of iron, oxide, and aluminum because that's what thermite's based on. But do you only have to use that? No, you don't. You can use a bunch of different little things. Molybdenum oxide, bismuth oxide, and copper oxide all actually do great jobs under here. And again, this is one of those pressure waves, the pressure of igniting it past the time that this is the ignition signal here, and then this is when it starts to go here. The aluminum and bismuth oxide actually had the highest pressure and fastest rise to pressure. So it's probably a slightly better material. The next one here is the copper oxide, which was the next one. But then there was a slight delay on the molybdenum oxide. Molybdenum is one of those metals that has a high boiling point and a really high melting point of its oxide. So it took a little energy to get that to start to react, and it gave off a decent pressure. Okay, notice this also. This is in 10 milliseconds right here. So it's a pretty fast reaction. Okay, so switching gears again, let's look at another way to measure some of your things for a nanothermite. And this one, I think it's still aluminum copper oxide nanothermite. This is very good. And they have an open acrylic tube. It's about 1.5 inches long. It's about 1/8 inch in diameter. And they pack it full, softly pack it full of your energetic material. They ignite it at one end, and then they use a 4,000 frame per second camera to measure the moving wavefront. And so you can measure the detonation rate by taking the little measuring on the camera. And so each of these are 0.125 second increments. So look how far it's moving across the system. Now, this is with both ends of the tube open, and so that we have no back pressure. It's basically shooting gases out the back end while it's doing it. This actually has one side closed. In fact, it has this side closed. So what's happening is it's only shooting gas out this side, and so it's having to propagate through something trying to force against it. And so propagate it into closed ignition. So, no, this one, they block the ignition side. So they block the ignition side, so it has to force itself through the material. That's right, sorry, backwards. And again, these are 0.2 seconds here. So at this point right here, it's actually burned all the way out the tube, and this is just residual material. Okay, so again, it's creating its own gases as it's burning. It's having to burn through the material as it's continuing until it gets to the low pressure zone. So you see a different burn. See how there's much more of burning taking place at the closed end of the pipe until it actually gets out into the pipe. So by measuring these high-speed things, we can actually look for that. Okay, so that's one way to do it. But there's a bunch of different ways we can intimately mix our oxidizer and our fuel. One way you can do it is you can actually do it with a vapor deposition technique. You're going to do copper oxide, aluminum, copper oxide, aluminum. You intimately mix them. You know exactly how much copper oxide you have, you know exactly how much aluminum you have. You don't have to worry about it aggregating. You just have to get it off your silicon wafer somehow. But I bet we can catch that off somehow. Anyway, so you can get perfect order of alternating silicon copper, aluminum copper oxide in there, and then you can get a good, and then by doing those thicknesses of the layers, you can get different detonation profiles. But what can we use these for? Well, I mean, if you want to use a nanocomposite just for heat release, you can use them for reactive bonding. There's actually pipes in this building. No, it's not this building. In the building I worked in the Navy, they had a crazy method for fusing all the plastic pipes together. So what they did was they wrapped 2 pieces of nichrome wire around each of the joints, closed the joint up, and then just hit it with a battery, and it melted the pipes together. And then you just have these 2 wires sticking.
Green rooms that way.
Oh, they did it. I thought they did something. Fuel was involved. Yeah. So that could be a nice way to do that right there. Micro-ignition or rapid initiation. Imagine you want to build a better bomb. You want to build a tiny little smart munition. Well, you have to have a little tiny MEMS thing to activate it or safety it or guard it. So you might want to do that. Micro power generation, micro actuation. I actually saw the silliest one in there is a micro actuator, where they have the detonable material in a membrane. It can expand. And when you detonate it, it forces water out of it. I'm like, okay, why would you want to do that? You can only do it once. Poof, squirt. All right.
For like,
Rebuild the thing.
for like emergency fire.
Well, I mean, it was on chip. It was like on chip. I don't know.
Well, so you wouldn't want, you know, plan.
Yeah, so I did something that I found that really weird. Reaction products, material synthesis. Think about it. We're making a bunch of really finely divided nano aluminum in there. And it's probably amorphous because it doesn't have time to crystallize. So you can do it for that. Inactivation of biological agents. So there's actually a different version of that we use. We use iodine for that. And you can actually like decon an entire area using a dental material, an iodine gas. So propellant additives, hydrogen production, nanocharges. So imagine you're Steve Jobs and they let you play with explosives and you're like, they're not going to copy my M1 chip. That's just going to blow up if they try to look inside. So anyway, so that's one way. And so this would actually work for that kind of application because you can bury it anywhere in there. Okay, so that's one way to do it. So let's see, we can mix things. We can do a solid gel. We can ball mill. We can do layer by layer. We can do, oh, let's see what else. We can also do that arrested reactive milling, okay? So in this case here, they're not going past the point where everything's gone off, but, oh, actually they did. They went too far because they're finding some copper here. But they started out with just copper oxide and aluminum, and then when they started to mill it without hexane, it didn't aggregate that much. Milled it with hexane, and then milled it with hexane a little longer. And what they got is, look how much more intimately the copper and copper oxide is mixed, although it's gone a little far because there's no copper. But I mean, compared to that, this one should burn a lot faster than that. That's big chunks of oxidized and fuel. So this is with that arrested reaction milling. But you know, hey, why not make it perfect? We can etch our copper and turn it into a copper oxide nanowires, and then we can plate on top of that another a shell of aluminum. So now we have an intimately mixed, and they're in a specific array. We could have them follow a pattern down the chain as it wants, or we could just clip them off and turn them into individual particles. But again, you can perfectly grow them exactly where you want. You know exactly how thick your layer of aluminum is. You know exactly how thick your layer of copper oxide is, and then you get some really good outputs. Right? So we have this one is with stored for 1 month. It still had a significant power output compared to the one that was freshly made. And then this is aged 1 month as well. So with just magnesium copper oxide, this is the stored. So what we're seeing here is we're getting a lot of power out because of that intimate mixing of oxidizer. What time is it? Okay. I'm not going to finish today. Oh, all right. So this one actually did a really good thing about comparing the different things, and it compared them to cost. Okay, powder mixing, pretty low cost. There's B mixers and a bunch of things like that. It's scalable. There might be impurities because you're doing it in a batch function. There's some safety concerns, but it's generally considered green because it doesn't involve solvents or heavy metals or stuff like that. Layer vapor deposition is expensive and difficult to scale, but if you want it for something small and smart, you're going to get something very high purity. They're inherently safe because they're out of oxygen, and they're inherently green except for all the power you use using your deposition. But again, it doesn't use a solvent or very small waste. Mechanically assisted, so that's like the ball milling systems, are medium to possibly scalable, possibly pre-reaction exists. If you go too far, it's not going to work out. Here, precautions are needed because you have to be very careful about where you go with it. And if you're only using powders, again, no waste stream. So the aerogels, it's technically a low cost and scalable. Serious impurities because this stuff, if you make it with just a little one, there's no guarantee all of your iron nitrate is converted. Right here, we'll have need precautions, and it's not green because it has a waste stream. And it has to volatilize your your solvent within the system. Porous silicon embedded oxidizers, that was like the one with the copper oxide wires. They can do it with copper, they can do it with aluminum too. They can etch silicon wafers in and put in little oxidizers on the chip. It's pretty low cost, pretty good. Impurities are possible. Precaution needed because, again, if you just rub the chip the wrong way, they go up. Literally, I mean, it's really cool. It's like a 4-inch wafer with a whole bunch of squares in it, and they deposit an oxidizer. And so that one would be medium green because you're actually having to deposit something. Do lithography. Self-assembly can be low cost in there, but our impurity comes from, you're doing difference. You gotta make sure everything's super pure when you're doing difference. Depends. If it's all water, it's probably okay, but if you have to use something other than water, we stop being green. Core shell nanostructures. So that's where you grow your aluminum and you grow something else on top of it as a particle. Usually it's in a spray type oxidation. And it can be safe, but it can also be very dangerous because when you're volatilizing off your materials there, if they, there's a possibility of static discharge. Difficult to scale up, very high impurity, and generally green, depending if you're using water in your system. So I thought that was a great little way to look at the different things that's possibly look up. Most of the ones that they do, they can actually do where they mix a metal oxide and some are an oxidizer with a binder. So there's two things you can do to enhance the reaction: is binders and fluxes. Okay, and then the reason they were looking at all these processes is they want to do an integration into metals. So they wanted to have a thing where in most weapons, you have a safe arm device. And so that most of the time they take the primer out of the chain of the explosives. Because without the primer, the main charge can't go off. So imagine having a little MEMS thing that goes, moves your primer out of the way, and therefore that becomes inherently safe. And then you have to have your little MEMS back in to make it go. So they were looking at these difficult things on how to introduce them into MEMS. And obviously the vapor deposition techniques, the lithography techniques, and the core shell structure, especially on flat surfaces. So then aluminum, copper oxide on a flat surface. So I thought that was a really good analysis on that particular paper. It looked really good about how they can do that. And here's one of the little MEMS devices right here. So in this right here, I believe the actual part that detonates is over here. You're actually using this to contract and move it in and out of the way of the main charge. The thing they're using here is a copper nanowires with aluminum, and then this is when they actually ignite. It's like a fluid snap. Okay, so let's go for something really dramatic. This is their graphic representation. It's in their thing. So what they have here is they want to say that we have our aluminum core, and then we're going to support our metal oxide around it using an organic framework. So it's a metal organic framework. So a lot of times you'll have a metal ion, and then you'll have a whole bunch of organic things sticking on a fairly regular basis. In this case, they say, if you heat it one way, it decomposes one way. If you heat it another way, it goes and does the thermite reaction and decomposes rapidly. Okay? So you can get some energy out at a lower temperature and some energy at a higher temperature. The total energy is higher for the whole set. But I mean, I thought it was a meteor when I first saw it. Or a cool rocket motor. So what they did was they created these things by having some rigid ligands, having metal salts, and the ligands they have are these natural product, I just forgot the name was. And so they should technically make these frameworks around there. Each metal ion wants to be bonded to 3 to 6 of the organic molecules instead of charge. Dopamine, that's it. So they take their nano aluminum, add some dopamine to help it adhere to the surface, and that's where the metal starts to sink. And so now you're starting to coordinate your metal all over where that system is. And then you can add your rod, your ligand system right here. So it's just the dopamine is just helping it stick to the particle. And then you add your organic framework to it. And then that supports all the metal oxides around the surface. So that was kind of cool. It looks pretty expensive to me, but kind of cool. So that's the same slide.
The illustration that they have presented.
Sorry, what?
The figures that they have made are good.
Oh yes, they're really pretty.
Yeah.
I am not that good at well, I would only do it in PowerPoint. Okay, so they said, well, okay, that's kind of cool. Well, so they grow kind of interesting. They grow like spherulites, where they're growing out from the center here until they get large enough. And we can actually see the little growing faces right here. We look at the surface of this. This is with the organic framework on it. It has a surface texture to it. These started as spherical aluminum particles, right? We don't have any, can't quite see how thick the layer is, but it has this very interesting texture to it. And then when they went and analyzed them to figure out where the copper was and where the nitrogen was, they looked at these things and they saw that they have coordination with the copper with oxygen, but they also have coordination with the copper and nitrogen. And so when they map the copper versus nitrogen here, they see it's evenly dispersed over the whole system, meaning the organic framework covers the entire thing completely. And they made it easy by this deposition, decomposition of iron with their structure to get to these coated systems. So I thought these are some of the coolest pictures that I've seen in front of the thing, because the way they grew into these, they're almost trying to grow platelets, just like some of those oxide ones, they grow platelets and they separate out. Okay, so did it work? Well, when they heated it at a rate here, they found out that they could get an increased temperature rise before the aluminum and copper oxide, or this copper oxide reacted. They would see a decomposition of the organic material in the framework. The metal itself was staying there. So what that did is that actually densified the material. And then once it got above that reacting point right here, it actually heated up and did the thermite reaction here. So we have two different decomposition mechanisms there. But the total energy that they got was tremendous. And notice that if you look at this, is a heat release image capture using an IR camera here, showing that you actually have it producing in the second level, producing gases that are lifting it off the surface. These are staying pretty much on the surface here. And these are being lifted off the surface in that higher temperature decomposition regime. Okay, so when they compared their work to others, right here, if you just burn nanoaluminum and oxygen, you get 584, I believe it's kilojoules. Sorry, I cut my units off here. Joules per gram. Okay, so that's really high energy density right there. And copper oxide, if they're both nano, you actually can do a pretty good job. It's about 1/5. If you do the layered one, like the vapor deposition technique, it gets a little higher. Another different process, DNA direct assembly. So they're using the DNA to do like the template, the oxide on the surface. Sonication of the organic material with perchlorate. So we've actually changed the fuel from aluminum to the perchlorate. And from this reaction right here, they see the ignition temperature is really low and the output temperature is really high. So just going from aluminum itself to this material here, you can set it off faster and get almost the same energy density out, because it's at perfectly, aligned nanomaterial, or it's, perfectly intermixed. Okay. All right. So now let's talk about other oxidizers. Right now, we've been talking about metal oxides and things burning air. So that's an oxygen, right? Well, that's not the only way to do these things. There are some other things that give off heat when we create a different bond. One of those in particular would be fluorine. Okay? In the case of TNT, it has its own oxidizer already in it. And so when you actually balance out the equation, you get a whole bunch of gases, a little bit of solid carbon here. So it doesn't need an external oxidizer. Okay, so an oxidizer is anything that can accelerate, burn, or convert something into a higher material that's giving off an excess of heat. Okay, so the first one I want to talk about is aluminum milled with PTFE, or Teflon, tetrafluoropolytetrafluoroethylene. In this case, what happens is the aluminum exchanges with the copper, the carbon, fluorine, it breaks the carbon-fluorine bond and makes an aluminum-fluorine bond, which just happens to be a gas. Okay, so this is just 10% Teflon that actually is used as a binder here. You can actually take that material, mold it into things, and when it detonates, it gives off a bright white smoke. Okay. So is fluorine the only one? No, other halogens work too. We use aluminum with iodine. This is not the one we use for ChemBio. ChemBio uses a different version of iodine. But the idea is you're giving off a lot of heat in the system here. Iodine by itself loses a whole bunch of mass just at 200 degrees because it's on its way. If you turn it into salt, this one does okay. But now, if you get this perfect balance between the aluminum and iodine 2, instead of actually, so that's aluminum metal and iodine by the diatomic molecule, they haven't reacted yet. Here they've reacted. Here they haven't reacted. They're much more stable. And then we can use that iodine as the oxidizer to give us our system. Okay. So why? Why should we look at this? Well, if we look at our different little things here, if we look at fluorine, oxygen, chlorine, sulfur, bromine, and iodine, all of these can be used as oxidizers. Okay, you can even make metal sulfides and other things like that. And what we see here is as you go up in size, right here, the chemical hardiness or the susceptibility goes down. Okay, what this means is that these will have stronger bonds with the things that they're bonding to. So what that means is that you're going to get more energy in a carbon in a something fluorine bond than an oxygen. Okay, so that means we can use any of these as oxidizers. Okay, so let's compare oxygen to fluorine. We got 2 minutes and I'll stop. Okay, so in the case of that, we're looking at enthalpies, and the more negative, the better, because this is the more heat released, right? Because negative is going to give us heat released. Right here, if we look at these smaller ions right here, we can see that the fluorides have a much higher enthalpy of formation than the oxides, meaning they're going to give off a lot more heat when they form. However, that's not so true if you look per cation. This is per cation here. And so we're looking at the mass of the ion changes. Here we're looking at now we have fluorine and oxygen 2, fluorine -1 and oxygen 2. And it kind of balances out with the idea that oxygen is going to end up with, you know, a -2 state. Fluorine's going to end up with -1 state. So the energy density is similar. And if you look at this, the one thing I want to look at here is this is the enthalpy of formation of the metal. Of the complex right here. And then this is going to be also the melting point. So when you have the different metals, aluminum fluoride forms, it has a very high melting point right here. But look at some of these other ones. Boron, it's a gas at room temperature. Fluorine, it is going to have a boiling point very high, but it's a gas at room temperature. Silicon, it's a gas at room temperature. This is a great thing to have. You're not fouling the surface of your particles. When you do these detonations, you're able to release energy. In the case of the oxides, all of the oxides melt about 450 degrees C. And they give off less heat when they do. And their boiling points tend to be very high if they boil at all. Okay, So this is saying that the oxygen would foul the surface of your metal as it burns, or the fluorines, a lot of them would foul as you do that. Questions? All right, I'm gonna stop there. It's 15. So, okay, let's see, how many? Oh, I have one more slides. Okay, so I'll finish this up after the first talks on Thursday. Okay, all right, stop sharing, stop recording.